So at this point, we've already talked about enthalpy, which is the heat content of a system, and we've talked about entropy, which is the disorder, the amount of disorder of this system. So now we're going to put those two things together and talk about free energy. So when we're talking about thermodynamically favorable processes, those processes that occur without outside intervention, they're going to lead toward or lean towards more or lower enthalpy, so negative enthalpy, which are our exothermic reactions, and they're going to tend towards more disorder, so a positive entropy, okay? So when we're talking about energy, we're talking about how much energy is available to do the work of the system. So our natural processes, our thermodynamically favorable processes, are ones that actually lower that free energy. Now we used the letter H to represent enthalpy. We use the letter S to represent entropy. We're going to use the letter G to represent that free energy that's available to do the work of the system. Now, if that sign for our delta G, our free energy, is positive, that means that the reaction is not spontaneous or not thermodynamically favorable. If the sign for our G, our free energy, is negative, that means that the free energy is being lowered, then our reaction is spontaneous or thermodynamically favorable. So there's two ways that we can calculate delta G. First is if I give you our change in enthalpy and our change in entropy, so our H and our S values, and then we can just use this equation, delta G is equal to delta H minus T delta S. Now, a couple of things when we use this equation. First off, the T, the temperature, has to be in Kelvin. So if we're given the temperature in Celsius, we have to add that 273 again, okay? Temperature has to be in Kelvin. And then our units for enthalpy were always in kilojoules, and our units for entropy were joules per Kelvin. And we usually will answer our entropy, or sorry, our free energy in kilojoules as well. So that means we need to convert our entropy into kilojoules by moving our decimal point 3 times to the left. Okay, 3 times to the left. So this chart is going to be really helpful for you guys in order to make a determination without actually calculating to decide if the free energy is going to be positive or negative. Okay, so first off, we're looking for whether or not the reaction is going to be spontaneous. And spontaneous means that it's going to be a negative delta G. So we're looking for which ones are going to have a negative delta G. Now, this reaction right here, this is what I said the processes tend towards when it's thermodynamically favorable. Exothermic reactions are going to have a negative delta H. More disorder is going to have a positive delta S. And that will always end up resulting in a negative delta G. Now, if you flip those signs and you look at this reaction right here, or this not reaction, but this line in this graph right here where the signs are flipped, this will never result in a spontaneous reaction because a positive delta H and a negative delta S is always going to be non-spontaneous, not favorable. Now you'll see the other two, if it's either both positive or both negative, it's going to determine or depend on the temperature, okay? Now remember, our formula is delta G is equal to delta H minus T delta S. So in order to have a negative delta G, we need to look at what these values are to determine whether or not it could end up resulting in a negative delta G, or spontaneous process. Now, if they're both positive, if the delta H is positive and the delta S is positive, the only way we can have a spontaneous process is at high temperatures. Because looking at this is going to be minus T delta S. So if that is high enough, then it could turn that delta G negative. Now, conversely though, if oops, I erased too much here. If they're both negative, if this is negative and the S is negative, then it's only going to be spontaneous at low temperatures because, again, when we subtract a negative here, minus T delta S, if we're subtracting a negative number, we can keep the delta G negative if this product is smaller than this negative delta H over here, okay? So when we look at this question here, what is the delta G of a reaction at 25 degrees Celsius if the delta H is 98 and the delta S, excuse me, is 292? So again, delta G is delta H minus T delta S. We have to convert our delta S, our entropy, into kilojoules by moving our decimal point 3 times to the left. So delta G is going to equal 98 kilojoules minus, we had to add 273, so this is going to be 298 Kelvin, times, oopsie, I don't know what I did there, times 0.292. So let's take a look at what this is. 98 minus 298 times 0.292. And we get a delta G that is equal to 11 kilojoules. 2 sig figs because of this 98 here. Okay, so 11 kilojoules. Now we have 2 questions to answer. Is the reaction endothermic or is it exothermic? Well, it is going to be endothermic because we have a positive delta H. So you want to make sure when you're answering these kinds of questions, you're looking at the correct thing in order to answer the question. Okay, so it's endothermic reaction because it has a positive delta H. This isn't one of the questions, but let me ask you this. Is this reaction spontaneous or non-spontaneous? The reaction is not spontaneous or not thermodynamically favorable because it has a positive delta G, okay? So would increasing the temperature have any effect on the spontaneity of the reaction? And the answer is yes, it would. Because if we have a high temperature, we could have a negative delta G. We'd have to have a high enough temperature to make that minus T delta S larger than the delta H. So our next question here, we want to calculate the delta G at 100 degrees for the synthesis of sulfur trioxide gas from sulfur dioxide gas and oxygen gas. So we have to write a reaction first. So we have sulfur dioxide gas and oxygen gas to make sulfur trioxide gas. Let's balance. So that should be balanced. We have 2 sulfurs, 5, 6 oxygens. All right, so when we're calculating this, when it's asking us to calculate the delta G from a reaction, we have to calculate our delta H and our delta S. So that means we have to look up H and S values. I like to look them both up at the same time just because I don't want to look back at this chart again. Now with the oxygen, let me talk about oxygen for a second, because we said that elements and diatomics don't have any enthalpy. They don't have any H values, but everything has entropy. Everything has entropy, even elements and diatomic molecules. So you have to look up everything's S value. So oxygen gas has an entropy of 205.07. Let's look up sulfur dioxide gas, and that has an enthalpy of negative 296.84, and it has an entropy of 248.9. 0.21. Looking up sulfur trioxide means we've got negative 395.77 as our enthalpy and 256.77 as our entropy. Now remember, we're going to multiply both of these by 2, except for the oxygen. So let's calculate our delta H first. So I'm going to do 2 times negative 395.77. And because I have to do products minus reactants, so I have negative 791.54 minus my reactants, so 2 times negative 296.84, and I get negative 593.68. So my change in enthalpy is negative 197.86. I got to calculate my delta S now. So I've got 2 times 256.77. That's 513.54 minus, I have 2 times 248.21. It's 496.42 plus 205.07. So when I calculate that, I got negative 187.95. And that's joules per Kelvin. So now I can calculate my delta G. Remember, that's delta H minus T delta S. So I have negative 197.86 minus 373, because I have to have my temperature in Kelvin, times, let me move my decimal point 3 times to the left, negative 0.18795. Don't forget that negative sign there when you guys are doing your calculations, okay? So negative 197.86 minus 373 times negative 0.18795. And my delta G, let me put this up here because I'm running out of room. My delta G is negative 128 kilojoules. So let's answer some questions here. Whoopsie. Let's answer some questions here. First off, is my reaction endothermic or exothermic? My reaction is exothermic because it has a negative delta H. Is my reaction leading towards more order or more disorder? It's leaning towards more order because it has a negative delta S. So it's getting less disordered. Is my reaction spontaneous or not? My reaction is spontaneous because I do have a negative delta G, okay? So make sure you understand what each of those values represents. Be careful when you're doing these calculations because there's a lot of little places where you can go wrong. So you just want to double check your work in your calculator, make sure you're adding everything correctly, plugging everything in, check your work against my key in your packets so you can make sure you understand what you're doing and reach out if you have any questions at all.